Okay, now for something completely different. So I'm going to go over the very basic theory of starshades for high contrast observations and give a very brief overview of their technological development. But I only have 25 minutes to cover both of these topics, so it's going to be a broad, shallow view, and we are not going to look at a lot of math. And in addition, my perspective here is one of an end user of devices like this, so not one of somebody who builds or designs these high contrast imaging instruments. So my goal here is to teach you how to use a starshade, not how to build one. And if you get really interested in learning how to build one of the world's experts on starshades is right up there. We can pick Jeremy Kasdan's brain afterwards. Okay, so just to give everybody a quick feel for how starshades work, here's a really nice movie that they made at GPL for the exoplanet probe starshade concept study that's going on right now. Okay, so starshade telescopes separate, starshade unfurls, it moves away from the telescope. The starshade is maybe tens of meters in diameter, and the separation between the telescope and the starshade is tens of thousands of kilometers. Move it into alignment with your target star, and poof, ta-da, there are your planets. All right, so that looks all pretty easy. Now, note, though, to align the starshade with the target star, this is something that's kind of weird to think about. To move to your next target, you have to slew the starshade to the next star over these arcs, tens of thousands of kilometer arcs. So the retargeting times are very long, weeks, days to weeks. All right, so starshades really do work. You use them very differently from the way you use a chronograph. So I'm just going to start by going over, just bullet pointing their different strengths and weaknesses. Okay, so first of all, one of the really nice things that is will be weird to think about is that the contrast and the inner working angle are now decoupled from the telescope size, from the telescope aperture. What this means is that, so the inner working angle is not proportional to lambda over d anymore. And what this means is you can pick your collecting area for the faintness of your planets, not for their separation from the central star. So in addition to which, starshades are inherently broadband. They have very high total throughput. They are not part of the telescope optics train. That fact also makes it so that they put very minimal constraints on other astronomical instruments that you might want to pack on the back side of this telescope. A starshade, we've put all the burden of starlight suppression is now outside of the telescope. So the instrument that you use for your exoplanet observations inside the telescope is a simple camera. Okay, they have no outer working angles. The field of view is simply just limited by the size of the detector. And you get a 360-degree suppressed field of view simultaneously, all at once. And probably one of my favorite features of starshades is that you've blocked all the bright light that you don't want before it went into the telescope. So you don't have a lot of unwanted photons bouncing around inside, and therefore you don't need a really high-quality telescope. So segments and obstructions, starshade don't care. Wavefront error, wavefront correction, not necessary. So basically you've taken all the technological burden off the telescope, put it onto the starshade. This is a feature that makes other parts of the astronomical community very happy. Okay, starshade drawbacks, though. They do have some that cannot be overcome simply with more technology development. So first of all, full-scale end-to-end system tests on the ground are simply impossible, given that to do it at full scale, your lab has to be tens of thousands of kilometers long. However, subscale lab and field tests are possible, and hopefully I'll have time to say a bit more about that at the end. Okay, so again, I mentioned there are these long times between the observations that you need to slew the starshade between the targets. A typical operating distance separation might be 40,000 kilometers. That would take you about a week to move the starshade to the next target. But that time isn't wasted. You can use the telescope for other things while you're moving the starshade. I don't know, look at a galaxy or something. So I don't know if anybody would want to do that. So the other thing, to move the starshade, you need fuel, you need propellant. So there are a limited number of starshade retargetings you can do. So, when you run out of fuel, you're done, unless you can refill the tank. But. Okay, so now I'm going to move on to some of the theory of starshades. I'm going to start really simple and try to add layers of more detail, more complexity as we go forwards here. So, okay, simple. Light from the star passing over your telescope. So you put your starshade in place, and you've cast a shadow. This is pretty simple. And a starshade really, I guess a starshade really is much more like putting your hand over the light source to see something faint, because in this case, your hand, is outside of your telescope. So the only criterion is that the starshade really, at this point, is that the starshade is larger than the telescope to make a shadow that's larger than the telescope, plus or minus some slop on the edge to allow for alignment error, or position error, in case your telescope moves around a little bit in the shadow. Okay, so now the inner working angle, it's really simple. So planets that are beyond the edge of the starshade, you can see them. So now it's just the angle to the edge of the starshade. It's the radius of the starshade over the separation distance. And you can change it by moving the starshade, by changing the starshade telescope separation. That's one of the other things I really like about starshades. They're not nimble, but they are flexible. Okay, so again, Earth at 10 parsecs, 100 milliarc seconds. If you have a 4-meter diameter telescope, a 6-meter starshade, if you just do out that equation, you get 6,200 kilometers. That's actually probably a little smaller than it needs to be, and we'll see why in a minute. Diffraction. Okay, not so simple. Diffraction. All right, so a circular, as Jeremy talked about earlier, a circular disk makes a diffraction pattern with a spot of Arago at the center, right? And this shadow just isn't dark enough to do exoplanet observations unless you make a circular occulter. It would have to be enormous, and it would have to be extremely far away from the telescope. So circular occulter is not desirable. But the solution to this was figured out, I guess, 1969 by Lyman Spitzer, right, Jeremy? Okay, early 60s by Lyman Spitzer, and the solution is to apodize the screen. So you make the screen have a smooth transmission that increases radially. But as Jeremy also mentioned, this is impractical to manufacture. So it was realized about, I guess, 2 decades ago, that you could approximate this apodized shape with these petals, with a binary starshade that had these petals on it. Binary meaning the transmission everywhere is either 1 or 0. Okay, so we put that in. Now our shadow has grown. The size of the shadow has gotten bigger because less light is leaking around. And now you can get better than 10 to the minus 10 contrast with a reasonably sized starshade. Okay, here's a little bit of math. This equation might look familiar because I cribbed it from one of Jeremy's slides. So here's the Fresnel diffraction equation, and this is what applies for the case of starshade and telescope. And we're not going to spend any time on the detail of this. I just want to define a few things. Okay, so again, still Z is separation between starshade and telescope. R, radius of the starshade. Rho, it's the radial position measured from the center of the shadow at the location of the telescope. And R is the radial position measured from the center of the shadow at the location of the starshade. Okay? And then the other important point is right here. This is the apodization function, A of R. Okay, so there's no actual closed form solution for A of R in terms of simple functions. And the way people have, but there are some various approximate and numerical solutions that people have used. I'm just going to only talk about the 2 most popular ones. Okay, so for the first one, Webb Cash in 2006 paper, he found an exact solution for A of R if you set at the center of the starshade shadow and also integrating to infinity, right? Yeah. And the function is a hyper-Gaussian. And then the other technique, which was pioneered by Jeremy Kasdan and Bob Vanderby, is to numerically calculate the optimal A of R by basically solving this equation at discrete points along the perimeter of the starshade. And then doing a bunch of math to minimize the transmission in the telescope at the telescope. If you want more detail, please read this paper. So, Okay, so now, though, I'm going to start to talk about the wavelength dependence of these two kinds of star shades, the hypergaussians and the optimals. Okay, so starting with hypergaussians. Okay, so with wavelength, at a fixed separation between telescope and starshade, in the red, the light diffracts more around the starshade. It leaks more around the starshade. You get a smaller shadow, which effectively means the contrast is lower. On the other hand, in the blue, the light diffracts less around the starshade. You have a larger shadow, and you get deeper contrast. So this basically tells you, for these hypergaussian starshades, they work at the wavelength, the longest wavelength you design them for, and they work that well and better at all wavelengths shorter. Okay, so what happens instead if we fix the contrast? How do we do? What happens when you do that? Because your fixed contrast in the red, that means we need to move this telescope into the deeper, fatter part of the shadow, which means reducing the separation. And when you reduce the separation, your inner working angle increases. Okay, in the blue, on the other hand, again, if we keep the telescope in the same sort of part of the shadow where the contrast is the same, we can move the starshade further away, and Z increases, and the inner working angle gets smaller. So basically, this tells you what happens when you change the separation. You also change the wavelength that you're observing at, and the inner working angle. Okay, so now I'm going to go into this a little bit more detail so you can sort of understand how these things work a little more quantitatively with some scaling relations. Okay, so first of all, this is a plot of log contrast as a function of Fresnel number and rho prime, which was that rho I said earlier, which is the distance from the center of the starshade shadow at the location of the telescope, divided by the radius of the starshade. And in contrast, we're a little trimmed off here. In contrast, we're going from 10 to the minus 7 in the dark red to 10 to the minus 11 in the dark blue. Okay, and this is you make one of these plots by solving the Fresnel diffraction equation that we had on a couple of slides ago, and this is the Fresnel number, just r squared over lambda times z. Okay, so and then here are the scaling relations that show that show how the other parameters of the starshade change. For a given wavelength and inner working angle, Fresnel number times lambda over inner working angle, z goes like this. They're really simple. Okay, so let's try and use this. All right, let's try a small starshade. Okay, with a 1.5 meter diameter telescope and a 5 meter starshade, that means sort of rho max, sort of the largest rho that you want to consider that light is getting into the telescope would be 1.75. That's the radius of the telescope plus 1 meter of additional slop in case you have position error. Okay, so if that's rho max, then rho prime max is 0.35. That's this line here. And basically what that's saying is that all the light at smaller values of rho is getting into the telescope. So this light gets in, that light doesn't. Okay, so say we want 10 to the minus 10 contrast. So that's the blue region in this plot. So let's look for the smallest Fresnel number that keeps us in this blue region. That's right about here, F11. Okay, so if you use those equations on the previous slide, just do them and set the inner working angle to what you want it to be, 0.1 arc seconds. You find that the separation distance is about 10,000 kilometers. And the wavelength, though, that this corresponds to is 0.22 microns. All right, let's look at another slice through this. Up here, say, where we're still in the dark blue region, getting nice good contrast here at this Fresnel number. Do the math again. The separation's still the same. The wavelength is 0.17 microns. Okay, so the bandpass of this telescope and starshade is all wavelengths less than 0.22 microns. So this sort of shows again what I was saying, that these hypergaussian starshades work, at the longest wavelength, and then better than that, all wavelengths shorter. Okay, but this is too short for exoplanet observations. This is undesirably short. This is getting into the ultraviolet. So let's try a different scenario. Let's try a larger starshade. All right, so now we'll bump it up by a factor of 3, 15 meters, and now the rho max hasn't changed, but the rho prime max has. Now we're at 0.12. Do the same thing again, draw our line across where we've got 10 to the minus 10 contrast. Same inner working angle. Now the F number is now lower. Fresnel number is now lower. And same inner working angle. Now the separation, the star shade increased by a factor of 3. The separation has increased by a factor of 3. And the wavelength has now gone to 1.15 microns. That's a good number. Again, just to verify all the rest of the stuff. At this other end, up at the large Fresnel number, the wavelength, the way up here, the wavelength is half micron. So that's a good bandpass. That's all wavelengths shorter than 1.15 microns. That's a good bandpass for doing optical imaging of planets. So this sort of shows you to get longer, to have a star shade that works well at longer wavelengths, you need to make the star shade bigger. So that's point 1. All right, so then now let's turn to how this differs a bit for these numerically calculated optimal star shades. So this is the same kind of plot of log contrast versus Fresnel number and rho prime. But now you can see that the shape of these contours has changed considerably. Before, the contrast was a rather weak function of rho prime here. Now it has this distinct shape. Okay, so a numerically calculated optimal star shade, the reason you do this is because they're smaller than the hypergaussian star shades are for the same contrast. And they also are less tippy. They have less their tips are less pointy, and that makes them a lot easier to manufacture. But the downside there is that these do have a short wavelength cutoff. Still, this is a very broad. I mean, remember, this is you keep the Fresnel number. Sorry, if you keep I've forgotten the equation now. But anyway, suffice it to say, wavelength is sort of decreasing down the plot here. So now there's a log wavelength cutoff here and a short wavelength cutoff here. Still, however, if you work this out, this is still a really broad bandpass. It's like 50% bandpass. So I mean, it's still really good. But it is just something to be aware of. Okay, so I'm going to just do the star shade behavior summary here. Okay. So redder bandpass needs a larger star shade. Larger star shade has to be further away to get the same inner working angle. Star shade is further away, you have longer slew times for retargeting. That's the price. Okay, the hypergaussian star shade size is set to achieve whatever contrast you want at the longest wavelength of observation. And then it works that well and better at all wavelengths shorter. For the numerically calculated optimal star shade, they're smaller for the same contrast and more buildable, but they do have a short wavelength cutoff as well as a long wavelength one. But they are still very broadband. Okay, so I'm doing okay on time. So now we're going to move to the technical challenges about star shades. All right, so first of all, that shape of that edge that controls the diffraction needs to be right. It needs to be very precise. You need a precise edge profile that about 50 micron tolerance over this rather large structure. The other issue is that the thin edge of the star shade also matters because you don't want sunlight in the solar system, scattering off the thin edge of the star shade and bouncing back into your telescope and destroying your contrast. Then there's also the on-orbit deployment of this large structure that has a precise shape. And then you need to align the star shade and telescope over these tens of thousands of kilometers distance. But this is only asking for a plus or minus 1 meter tolerance. And I'm told this is not especially challenging and that we do harder alignment control problems every time we dock at the space station. So I'd say this is a soft requirement, and we could maybe make that a little tighter and get away with making the star shades a little bit smaller. Okay, so here's what's going on to deal with these problems. Precision petal manufacturing. So this is about the shape profile for the star shade. So at JPL, I can't remember what year it was, but suffice to say, they built a full-scale petal that has, it's an optimized star shade shape that has the edge profile that was needed for contrast of 10 to the minus 10, and they measured that edge profile and proved that it actually did have that shape. So, ta-da, that's great. And here's a picture of, let's see, it's Maggie Turnbull, Sarah Seeger, and me holding the petal. It's very light, and we're a portion of the Exoplanet Probe Starshade Science and Definition Team. Then about the other issue, about the thin edge of the starshade, NASA has funded some work on development of making that, basically it's a very black razor blades to put around the thin edge of the starshade. So that work is in progress. Okay, deployment. Here I think a picture, a movie, tells 1,000 words here. I'm just gonna let it run. So this is also a JPL. Again, I don't recall what year this was done. Okay, two summers ago then. So anyway, so there's full-scale truss with 4 petals only. And there it goes. So obviously there are some unrealistic aspects in this deployment demonstration. For one thing, we're not going to have humans mediating the deployment unless we can get the astronauts involved. So that would be cool. Okay, so ta-da, it deployed. And they did it over and over and over again, and it deployed and deployed and deployed. No failures. Okay, and then, all right, so now I'll talk just a little bit about what has been shown for actual contrast performance with starshades. All right, so the first part, so distortions, like wiggles, waves, bends, tip clips and stuff like that, have been incorporated into optical models. And those have shown that you can get, theoretically anyway, 10 to the minus 12 contrast with a, buildably sized starshade. Okay, and then in the labs, the starshade testbed at Princeton, at about roughly 0.1% scale, that's in monochromatic too. That's important to say. They achieved a monochromatic contrast of 10 to the minus 10. So the black regions here are 10 to the minus 10. And all of these actual bright spiders, bright parts here, are due to the fact that they were not actually in space, and they needed something to hold the starshade up. So these wouldn't be there with a space starshade. And then some other testing that I think is actually rather fun is this 1%, roughly 1% scale field testing that some people from Colorado and Northrop Grumman are doing. And so this involves taking telescope, starshade, some light sources, going out to a big flat desert place and setting them up with roughly kilometer separations between them, and just turning it on and trying it. And so these use hyper-Gaussian starshades, right? I think they do, yeah. And so here's an image from one of those field tests. So first of all, so there are some these speckles here, and this sort of halo. The halo is actually coming from dust in the air at this this dry lake bed, which actually will happen in an exoplanetary system too. That would be the exozodiacal dust. So interesting little analogy there. Then all these little speckles here, I guess, those are from edge errors. Right, that's a 10 to the minus 5 planet. It's booming, obviously. Right there at the edge of the starshade is a 10 to the minus 8 contrast planet. Now, it maybe it doesn't look much brighter than these speckles, but it would be very easy to distinguish this from the other speckles if you rotate the starshade, which is not something they can do while they're holding it up on a tripod, but it is something we would definitely do if we were using one in space. Okay, and actually, I'm good. I'm done. Awesome. Great. So, and right here are the references for more info. I'd call these some of the seminal works on starshades. Hyper-Gaussians, numerically optimized. This is about error budgeting and about technology, recent progress on technology development. So, and if you have any really, really detailed questions, ask Jeremy. So, right, done. To be quite frank, we're just sort of right now starting to figure out what they actually cost. And it's part of this exoplanet probe study that's going on right now. We're in the middle of the aerospace costing process. So I don't know yet. Well, okay, Keith Warfield from JPL, he has a guess at what he thinks they cost. That is, you'll see if you go to the hands-on session this afternoon, and you'll see it in the costing spreadsheet. But that isn't like aerospace blessed or anything. That's Keith Warfield's estimation. But yeah, I mean, there's no reason. If you have two star shades, that really increases your observing efficiency because while you observe with one while you're moving the other. But, you know, frankly, the general astronomical community doesn't actually typically favor that because they actually like the notion of being guaranteed that we can't spend all the telescope time on exoplanet observations.